Okay, hello again. So in this section, we are going to look at the software process activities. I'm just going to turn off my webcam just because I don't want it to be a distraction to people. Okay. Right, so we're essentially just going to focus on the key software process activities that are associated with whatever software process model that you end up using. So irrespective of whether you're looking at or wanting to use the waterfall / traditional model, whether you're using an agile technique like Scrum, or if you end up using or you take the approach of integration configuration, you pretty much go through these different software process activities, right? So we'll look at this whole idea or notion of requirement specification or requirements engineering, design, implementation, and then verification and validation, right? Okay. So the thing here is that in a real-world setting, the different software processes are actually interleaved, right? So they involve a sequence of different activities that might be technical in nature, that might involve working with other people, so you end up collaborating with other people, and also activities that might involve some notion of management, right? So these would be like managerial activities that may not necessarily be technical in nature, right? So things to do with the budget, for instance, timelines associated with the project, right? But the thing with all these different activities is that they're all done in conjunction to try and work towards a broader overall goal of the project, right? And the goal really is to come up with a robust software specification, an appropriate design of the system or software that you're wanting to develop, and then specifics of the source code associated with the software that you want to develop. So actual executable programs associated with the software. And finally, details to do with the testing of the software. So essentially, these you go through these interleaved activities in more or less like a cyclic nature, where you initially, which is almost always the case, you collect the requirements, you design, you come up with the design of the system or the software. You come up with the actual executable source code, which is mostly involves programming here. You perform some sort of test to ensure that whatever it is you are implementing, whatever it is you've implemented here fits or is associated with the actual specifics highlighted by the eventual end users of the software. And then finally, you go through this process of evolution, because eventually, as time goes on, you might be required to make changes to the software itself, right? So changes occur, bug fixes, and security patches and things of that nature. Remember what happens in Windows? Those security updates that you normally need to download and install something. I hope that rings a bell. Okay. Right, so like we said here, you essentially the key activities here associated with requirements engineering, design or development, validation, and then evolution, right? While all these different process activities are pretty much found in all the different software process models, but the way in which they are used is somewhat different, right? So for instance, when you decide to use the waterfall model, the traditional model, these different activities are organized in sequence, right? So one activity needs to be performed before the next one can be performed, for instance. If you, on the other hand, leverage incremental development, then you go through a process where you quickly go through these different process activities for each software iteration that you go through. So if you plan to go through 3 iterations, you come up with, I guess, a feasibility prototype, an intermediate prototype, and then the final system, then each of these different iterations will involve these different process activities. So iteration number 1, you go through this cycle. Iteration number 2, you go through this cycle. Iteration number 3, you go through this cycle as well. Okay, so the question then is, what exactly happens in these different process activities? So we'll go through them in sequence, right? The first phase is certainly requirements engineering. And in particular, a thing worth mentioning here is that requirements engineering typically involves 3 different sub-processes. So requirements elicitation and analysis, requirements specification, and then finally requirements validation. We'll go through all these 3 different subcomponents so that we understand what exactly goes on here. Right. So elicitation and analysis, essentially, it's the first phase of the requirements engineering process, and what typically happens here is you go through a process of gathering the requirements from the customers, or otherwise the end users of the system or the software that you are wanting to implement or develop, right? And so you typically go through a process of observing how these customers or users conduct their day-to-day business, in the hope that you'll be able to extract useful information that you feed into the overall design development of the software. Right, so you observe the users, and in certain instances you also interact with the users, right? It's also fairly common for, and quite useful actually, to come up with an initial prototype that you expose to the users, right? So the idea is to actually have the users get a feel of what the system that you're wanting to develop is going to function like, right? This doesn't necessarily have to be an executable product. In certain instances, it could be something as simple as a paper-based prototype, right? And actually, there are actually tools that you can use for these things. Wireframing tools, for instance. And some people have actually made use of very simple techniques or simple software tools like PowerPoint, for instance, where you just draw up some wireframe of how the interface is going to look like, and then you use that as a tool to try and explain to the user how the software is going to function. Just to mention here that we have dedicated lecture series for prototyping and for requirements engineering. So this is meant to just give us an overview of the different process activities. Okay, so once you go through the requirements elicitation and analysis step, you obviously come up with a very high-level description of what the system is going to be like. And the next step really involves formalizing or coming up with a formal document that is going to incorporate the requirements that you'd have gathered from the requirements elicitation and analysis phase. Right? This is where you actually come up with a formal document that is going to include all the different types of software requirements, right? And typically, these would be separated into either user requirements or system requirements. I guess sections of the document might also highlight functional requirements and non-functional requirements, right? But we have a dedicated lecture series where we discuss all those different things, right? And then finally, once you come up with this formal specification or the requirement specification document, what you want to do is to make sure that you validate the requirements that you'd have gathered from the users, right? And the reason you want to do this is you want to make sure that the requirements that you've gathered are correct and comprehensive, right? You'll notice here that the requirements elicitation analysis phase provides or acts as input to the requirement specification phase, which in turn provides or serves as input to the validation process, right? All right. And then finally, the next step after requirements engineering or requirements analysis is software design and implementation. In certain instances, these two will be separate entities, but in certain software process models, these are more or less viewed as one logical activity, which is why they are combined into one activity in this slide, but it doesn't matter really. So the design and implementation essentially involves you coming up with the actual executable software, right? That hopefully the end user is eventually going to use, right? So you go through a process of coming up with software design document in certain instances that provides design details. So it could be architectural designs, for instance, of the software that you're wanting to implement. And the design really is nothing more than, I guess, a logical structure that spells out details associated with the requirements specification, right? And then obviously you go through the implementation phase, which involves converting the logical structure coming in from the software design phase, the software design process, into the actual executable program, right? So as earlier mentioned, I mean, these two activities are more or less like closely related, and so are usually interleaved, right? All right, so the question though is what exactly happens in the software design process, right? So it's block diagram here from Ian Summers' book here, the prescribed reading, kind of highlights the key things or key aspects associated with the software design process, right? So you typically have inputs, so things that you want to feed into the overall software design process. And then you have individual design activities, right? And then finally, the end result is these design outputs. So we'll go through these things in sequence to try and appreciate what exactly all these different aspects involve, right? So we'll start with the input, right? So obviously, seeing as you're developing software, we do know by now that software just doesn't function in isolation. Typically, this software is going to have to be executed on some hardware platform, right? And we know by now that there are different hardware architectures out there, right? And so when it comes to platform information, really, some key things that you would end up feeding or collecting to feed into the overall design process are things specific to the hardware architecture where the software is going to be executed, right? Is this hardware platform going to be modding out here, but is it going to be a mobile? Is it going to be executed on a mobile device, for instance? Is it going to be executed on a particular hardware architecture? Is it going to be 32-bit or 64-bit architecture, for instance, right? These are all things to think about. And obviously, we know that the software has to be interfaced with the operating system for it to be able to control the hardware, right? And so something else that needs to be fed into the overall software design process is specifics of what sort of operating system this software is going to be installed on, right? And then finally, the potential external services and APIs that are going to be interfaced with the software. This is increasingly becoming common, right? So these days, it's almost inconceivable to have software that doesn't interact with external services out there, right? If we were to cite examples that are closer to home, for instance, like say Moodle, for instance, you notice that Moodle has a mechanism in place that facilitates the interaction of APIs associated with web services linked to Dropbox, for instance, and Google Drive, right? I'm not sure if our student information system, SIS, is interfaced with any external platform, but I'd like to think it is. Okay, so the other input that you provide to the software design process is obviously the things coming in from the previous stage. This would be the requirement specification document, right? And you're looking at providing details associated with the user and system requirements associated with the software that you're wanting to implement or develop, right? And then finally, in the event that you are developing a database-driven application, you obviously want to provide a description of the data that the software is going to be operating on, right? Just to mention here that it's almost unheard of in 2020 to have an application that is not database-driven. I mean, they're probably there, but most sophisticated pieces of software will essentially involve the use of a database at some point. Right? All right, so in terms of the different design activities that you perform, it turns out that there are different designs that you need to come up with, right? And we'll go through all of these in sequence so that we have an appreciation of what they entail, right? So essentially, really, some of the designs that you need to come up with is the architectural design, the interface design, right? The component design, and if it's a database-driven application, the actual specific database design. Okay, so when it comes to the architectural design, what you're doing really is to go through a systematic process of coming up with a design of the system structure here. And what you do with the architectural design is you highlight the key components associated with your system, right? These high-level components and the relationships that exist between those different subcomponents. The interface design activity will involve you defining the various interfaces that are associated with the different system components. And more importantly, really, things to do with the graphical user interfaces. For instance, if you're when it comes to implementing the part of the system that the end users are going to use as an entry point to interacting with your software application. So this might take the form of coming up with very simple things as identifying widgets that you're going to associate with the user interface, right? So what sort of buttons and text fields, text areas, combo boxes are you going to include on your system interface, right? It turns out this is an art. There's a whole computer science subfield called human-computer interaction. And even though we don't really focus a lot on that in this course, I think we'll probably introduce aspects of HCI so that we have an appreciation of how important this whole process is. And then obviously, like I said, if the software implementing is going to be database driven, you want to come up with a database design, right? Essentially, you're coming up with these different data structures that are going to define how your data is going to be represented in the database, right? What sort of relationships exist. A caveat here, a side note, you're probably going to have a lengthy discussion of database design. Specifically, you're going to learn how to come up with so-called ER diagrams or entity relationship diagrams in, I believe it's 3010. So brace yourselves, it's a really interesting course, right? And then finally, you obviously need to go through a process of or an activity that involves you designing the different components associated with the software, right? In the event that you are leveraging integration and configuration, the integration and configuration software model, this would probably involve activities like going out there and identifying reusable components that you'd potentially integrate with your software application. And obviously, if those components don't already exist, then you come up with specifics on how you go about designing those reusable components. All right, so in terms of the outputs coming in from these different design activities here, this is, I guess, a bit intuitive here. 4 key outputs here, right? So the architectural design is going to result into system architecture. The database design will enable you to come up with a robust database specification. The interface design process will come up with interface specification, and finally the component design will yield the component specification, right? And really, it's not like you'd more or less like have separate documents that will have all these different outputs. It's usually the case that all these 4 key outputs will be embedded within a so-called software design document, right? So this is one comprehensive document that will have all these different designs, right? All right, so I thought now would be a good time to cite some examples associated with the software design process, right? We'll use a slightly different example here. So the University of Zambia, like most institutions of higher learning, makes use of or makes available research output by using so-called institutional repositories. And just so happens that UNZA's institutional repository is implemented using a commercial off-the-shelf application called DSpace. And for those of you that are wondering, DSpace is available for free, and it's also open source, right? So you have access to the source code, and you can download the piece of software for free. And more importantly, you can also contribute to the overall success of DSpace. So you contribute by way of providing source code or enhancements to the application. Also, just a side note here, works are underway actually. I think development is underway for DSpace version 7.0 or something. Okay, so just a simple example here of the architectural design associated with DSpace. So this slide just showcases the system architecture associated with DSpace. You notice that this particular system architecture highlights the different components associated with the 3-tier architecture used by DSpace, right? So 3-tier in that you have the application layer, the business or logic layer, and then the storage layer here. And then you have the various subcomponents associated with each of these different tiers here. Alas, I think I do apologize for this. Sadly, this system architecture doesn't show the different relationships that exist between these different layers. But there is actually exchange of information between these different components. So for instance, the application layer does not directly interact with the storage layer, but rather goes through the business logic layer, which in turn sends whatever message is coming from the application layer down to the storage layer. Right? If you're interested, we can have a lengthy discussion about how these different subcomponents actually function as well, but that's besides the point. It's outside the scope of our discussion. And then I thought I would also provide an example of still on DSpace of the database design. So this screenshot essentially shows you a rather complex ER diagram associated with the DSpace database. Quite complex, really. You soon learn in EDU 3010 that each of these block diagrams here represent an entity. An entity will usually translate to a table that stores data in the database, right? So you can see that the database associated with DSpace here has quite a number of tables, right? And so these arrows here essentially spell out relationships that exist between the various tables here. Good stuff. Okay. Hopefully that was clear. And then when it comes to the system implementation, like I said, or as earlier mentioned, this process essentially just involves actual implementation of the program executable itself, right? Or the process of configuring the application system. This is the artifact that ends up being installed on the customer or user machines, and the user eventually interacts with the software that way. Again, just to underscore the fact that the design and implementation activities are interleaved, right? for most types of software, depending on the software process model that you might adopt. And also to remind us that typically, seeing as the system implementation involves programming, a reminder that programming is fundamental and individual activity. So if you have a number of people that are writing software programs associated with a particular piece of software you might be implementing, must appreciate the fact that these individuals will typically be working in isolation, right? And this applies to the various projects that you're working on, right? We said a minimum of 4 to 5 individuals, but once you start once you start programming or writing programs associated with the various components of the project you're working on, you'll be working in isolation. Right? Another point to have examples on this, we also have a lengthy discussion on how to take advantage of software configuration management when working as part of a large team. Right? So another reminder that the system implementation will typically involve, when you're programming, this would typically involve debugging of the software programs that you might be implementing, right? To try and detect potential faults associated with your programs, right? When you're programming, this would obviously involve things like unit testing. Hopefully you still remember this from 2010, which was last year, right? Okay, so I thought I would also highlight a few examples associated with aspects of implementation that we just discussed, and we'll still continue off with DSpace here. Like I said, DSpace is it's a classic example of a free and open source software application. And so this URL here, this screenshot shows a homepage for the GitHub page for DSpace, right? It has certain interesting things here, like the number of commits, right? Changes made to the piece of software. So it's about 12,200 commits, which is a lot. Number of different branches associated with this piece of software. We have a discussion of branches when you're looking at software configuration management. So don't worry about this for now. You soon understand all these different things. The different releases of the software. What you need to appreciate is that the current stable release for DSpace is version 6, but you have to appreciate the fact that there was probably version 1 at some stage, right? And in fact, the way versioning is done for DSpace and most pieces of software is you just don't jump from version 6 to version 7, right? You typically have intermediate versions, maybe version 6.1, 6.2, 6.3, 6.4, which explains why there's a total of 96 releases associated with this piece of software. And then more importantly, you notice that the number of people that have so far contributed towards the overall development or implementation, actual writing of software programs or software code, is a total of about 134, which is a lot. This is a really very popular piece of software here, right? And so remember we mentioned earlier that programming is an individual activity, right? So a question to ask is, how exactly do you go about harmonizing, different contributions coming in from different programmers, right? It turns out that it's fairly common to come up with a set of rules that dictate exactly how people interested in contributing source code will go about doing that, right? So these will range from specific guidelines associated with the style, right? How do you name variables? How do you structure the code? Do you use things like tabs as opposed to spaces, for instance? Those are all important things to take into account when you're working as part of a large team. Okay? And again, I am bringing all these examples up because you, as you're working on those different projects, you're working as part of a fairly large team, right? 4 to 5 individuals. At some stage, you're going to have to come up with a coding standard that you're going to follow. Naming conventions. So how do you go about naming variables? How do you name functions? How do you name classes, right? how do you provide comments in your code so that your other colleagues are able to follow through with what exactly you are doing when you are writing some part of the software system you're implementing. Right. So for this space, I thought I would highlight the fact that there's a coding style, right? Specific details on how you write these different pieces of software. It just so happens that this space is implemented using Java. If you're interested, I do encourage you to go to this URL to go and look at details associated with the coding style, the DSpace coding style. And perhaps, who knows, maybe your group, right, might decide to adopt this particular style instead of coming up with a completely new style of your own. I do this myself a lot. So the coding standard that I use, I did not develop on my own, but rather just cherry-picked from already existing coding style standards. All right, so and then finally you go through this process of verification and validation, otherwise called VV. And the reason why you want to go through the verification and validation process is you want to prove or to test that the software that has been implemented actually conforms to the user requirements. Remember, we went through a process where we gathered requirements, we came up with a requirement specification document, come up with the design, and then we implement the software. The question to ask though is, does the implementation match with what the user requirements are or were, right? This is the whole point, one of the reasons why you go through a verification and validation process. And really, you typically go through an end-to-end process of just verifying the different processes, and you also do a lot of system testing, right? This so-called system testing can take the form of you coming up with predefined test cases that match with the requirement specification, and this typically involves real-world data, right? So you use these test cases, you execute the application using these test cases to try and test to see if it meets the requirements. And just to mention that even though there are a number of verification and validation activities, but typically testing is the most common and most important part of the verification and validation process. Just because what you're doing is testing to see if the implementation is a direct match to the requirements, right? Is the reason why you're testing. Okay, good stuff. Again, just to mention that we have a in-depth discussion of how you go about coming up with test cases, different VV activities or verification and validation activities that are out there. So don't worry, again, a reminder that we're just glossing over the different process activities, right? Eventually we have a lengthy discussion of all these different things we're discussing. So in terms of the stages associated with what we're saying, the most common and most important part of verification and validation, which is testing, you typically go through process of performing component testing. Remember, we said at some stage during your design, we go through a process of coming up with component design, right? So the question to ask is, do those individual components that you've designed and implemented, do they work as expected, right? So you verify that by doing component testing. After component testing, obviously, you test the entire system as a whole. One of the reasons you want to do this is to verify or confirm that the interaction of the components works as expected or as anticipated. And then finally you expose the system to the user so that you expose the system to the user for the users to formally accept the system, right? So this is called acceptance testing, right? Usually involves the customers or potential end users of the software application. So if you were the one implementing SIS, once you do component testing of SIS and system testing, you expose SIS to the users, which should be the students and faculty staff and support staff, and all that involves acceptance testing, really. So like I said, with component testing, you're just testing the individual components, right? And then for system testing, you're testing the entire system as a whole. And then acceptance testing involves, the customers or end users taking the software for a test drive, essentially, to confirm if it actually meets their needs. All right, so if you were to look at the bigger picture here, this block diagram here helps explain what typically happens, right? You notice that acceptance testing gets input from the requirement specification. Remember, you're involving users here, so the question is, does the system work in accordance with the user requirements, right? The system specification is also fed into here, so are the details that the users expected the system to exhibit. Do these conform, right, to the actual implementation of the system? System integration, which really system testing here. Input comes in from the system design, overall system design. This will be architecture design, database design, the system specification, right? And then finally, this is subsystem integration, which is essentially you'd be testing the integration of the different components associated with your software system or application, right? So input comes in from the detailed software design and the system design as well. And finally, you're looking at module and module testing or unit testing, right? You're looking at actually testing the actual programs that you're writing, like different modules and classes. We will go through examples on how to do all these different things, different documents that you come up with, acceptance test plans that you need to come up with before you perform most of these tests in due course. We might look at unit testing, but the assumption we're making is that this was done in 2010, right? But if need arises, we'll also cover this as well. All right. So you notice that component testing, system testing, and acceptance testing all feed into the overall service exhibited by the software application that you'd have implemented, right? So again, back to our DSpace example here. DSpace, like I said, is a free and open source software platform. So most of the testing is typically done by end users of the application. And what typically happens is if end users notice that there's a glitch or a problem with a piece of software, you can easily open an issue, right? If it's a bug, then you open an issue. This can be done using DSpace. And I think they also use, this is using GitHub, but they also use Jira, I believe. So you can log these requests. And then the programmers, remember the programmers, these individuals here, these 134 individuals will be able to respond to the issues raised, right? The reason I'm using this as an example here is because it's a generic commercial off-the-shelf application. There is no explicit customer that this software is being designed for, right? So people from various domains end up using DSpace, and so the only way you can fix problems, or you can test the software is by exposing it to the broad spectrum of potential users of the software. Okay. And then it's also worth mentioning that once you're done, so we've discussed requirements engineering or early stage analysis or requirements analysis. Then we went through software design, implementation, and then testing. But remember that we are going through a loop here, right? You must always remember that the software process activities are interleaved, as we said, right? So requirements analysis, design, implementation, testing. Once all these things are done, you go through an evolution of sorts, right? An evolution process where you might end up coming up with bug fixes once users notice to say there's a potential bug that wasn't picked up during acceptance testing, for instance. The evolution process might also involve implementation of new features for the software application. UNZA's SIS platform might work just fine now, but 5 years down the line, perhaps UNZA will have a unique set of requirements, and some might need an additional feature to be integrated with SIS. All that is going to be part of the evolution process where you again go through this loop, right? So hopefully that makes sense. Sorry for the back and forth here. Okay, so we're saying, like I said, requirements change with time, obviously. New business rules are integrated in these various domains, and so obviously those need to fit into the different software packages that might be used by that particular entity or company or organization. All right, so in terms of the software evolution process, obviously, I guess this kind of block diagram helps explain what typically goes on here. Once you initially gather the requirements, you come up with the design, you implement the software, and then you verify and validate the piece of software. As you're going through the evolution process, what will typically happen is, as business rules are changing for a particular organization, new system requirements would need to be defined, right? Those new system requirements will feed into that existing application that will have been implemented. And then from there, these proposed changes are formally accepted. You modify the existing system, and then you loop back, right? Sometimes it might just be the case that perhaps the proposed changes will mean that you need to come up with a completely new system. Then you branch off here, and then you continue looping, right? Okay, so hopefully this makes sense here, right? Also, this block diagram really could be viewed as incorporating the different activities associated with implementation of the system from the onset, and also in combination with integration of proposed new changes to that particular system, right? So when you're implementing the system for the first time, you obviously have to go through the requirements engineering process, right? You define the system requirements, to see if there are any existing systems that exist. Then you come up with system changes. If need be the case, you modify the system, and then you loop, right? You're going through an evolution process. Otherwise, you come up with a new system, right? Hope this makes sense. All right, so just to recap what we've discussed so far, we went through a lengthy discussion of trying to highlight the core process activities associated with software development, and we really zeroed down or narrowed down on the requirements analysis and specification phase, where you go through a systematic process of identifying the customer requirements or customer needs insofar as the software is concerned. And then you come up with, so this requirement specification will feed into the design and implementation phase, where you come up with these different artifacts that spell out the different high-level components associated with your application, right? So we also spend time discussing the different designs that you might come up with. So architectural designs, database designs, interface designs, and component designs, right? And then finally, you go through a verification and validation process to try and ascertain the fact that the user requirements have actually been met, right? And to actually verify that the software works as expected, right? We made mention of the fact that this verification and validation does not necessarily just involve you interacting with the users, but it also involves processes associated with unit testing, right? So programmers testing or verifying that the source code that they have written actually functions as expected. And then finally, we actually went through a process or discussed at length the software evolution process. So hopefully all this makes sense. If not, we have dedicated lecture series where we discuss all these different process activities at length, right? I think in next lecture series, if not lecture series number 4, will actually involve requirements engineering. All right. So in the next lecture series, we'll go through or explain exactly how we go about coping with changing requirements or changing customer needs, right? Thank you very much, and I'll see you in the next section.